pictures in the book actually. If you can, for example, if you have all books with you, so look at the picture 3.11. 3.11. Look at the picture 3.11. So this is what the area that you want to compute, right? And when you are trying to compute, for example, the Riemann integral. So imagine you split it into the rectangles. So I split it into the rectangles, okay? And now I am throwing that onto the wall actually, so projecting it onto the wall. So you will see that some of rectangles has become distorted actually. Some become little, some become big actually. So they are not uniform. So in other words, just directly computing the Riemann integral is going to be a bit troublemaking. Okay, so what should be the definition then? How to compute the area under such kind of a curve that is, hanging in this space actually. Okay, so that's what we like to do. So let's develop a definition for it. Okay, I don't want to throw a definition. I want to show that why this definition is the way it is actually. All right. So again, I have a scalar field, and that's the domain of the scalar field. And in this domain, there is a curved line, and I'm operating f onto this curve, and I'm getting a curve in this space, and I'm interested in computing the area under this curve in this space actually, which has not only curvature, but it also has torsion actually. In other words, it's turning and twisting. These are two things actually. Okay, it's turning, and so when you are drawing a curve in 2 dimensions, so it's turning up and down, but I can't see the twists here actually. Twists here. So the curve can have twists in this space also. Okay, there will be an entire course on what you call the differential geometry, in which you will basically, learn about the turnings and the twisting of the curves. So, beautiful kind of subject. So I am interested in what? I am interested in computing the area under f. So if this is f, I am interested in computing this area actually. The question is, how can I compute it? Okay. This is going to be can be done when you're going to involve that how this curve is changing in this space. In other words, you have to involve in your definition the derivative of the parameterization actually, or the path. Okay, that's what we like to do. So, okay. So this is my wish, f of p of t dt. Okay, so I would like to calculate area under such kind of a formula, but I know that this is a bit troublemaking. I'm losing some area actually if I'm trying to calculate the area. So how can I make it better? Okay, what parameterization should I put here in such a way that that you get the exact area rather than just choosing this parameterization. Okay, so the remedy comes from that. Try to make this function dependent on the arc length actually, okay, or the natural parameterization of it. Okay, so I know that what is arc length at any time t or at any point p from a to t. So a could be, okay, so a to t means that I'm interested in computing the area under an arbitrary point actually t, where this is like f of p of t. Okay, f of p of t. So integrating by a to t means what? Okay, so you have to keep in view this curve is even coming through an interval a to t. So I'm saying take a to t. This is going to give me a part of the curve, and when I project it into 3 dimensions is going to give me the part of this space curve actually, or the scalar field defined over the curve.
अच्छा सर वो इसमें पार्ट नहीं है, वो पार्ट ला रहे हैं इसमें जो टर्न और ट्विस्ट नहीं हो रहा.
Let's see how it goes. Let's see how it goes. Okay, so I'm not talking about, so again, you know, don't look at my picture actually. In the sense that they,
जहाँ पे टर्न ट्विस्ट नहीं हो रहा वो उनको पार्ट्स में डिवाइड कर.
that could be one trick actually. That could be one trick, okay? You know, you just see that as you know, and this would be a good trick actually, that you split the area into the parts where you know it's start changing its behavior actually. Okay. Anyway. So let's think about this. Start with the parameter s of t. So s of t is a of t, p prime of t dt. Okay. And there is no reason that why I shouldn't be able to differentiate this s of t. Okay. The fundamental theorem of calculus allows me to, you know, derivate such kind of functions. So if you have an integral, you can differentiate the functions. So it's going to be s prime of t is going to be what? So it's going to be, you can say it's going to be p prime of the t, and this is true for all t in the interval a to b. Okay? And I know that this number is positive always. So p prime of t ka magnitude is what do you call positive. So if it is positive, then what can I say about s prime of t? Then it must be increasing actually. I know that if a function has a positive derivative, it must be increasing. So s is increasing. S is increasing. Alright? So if a function is increasing and derivative exists and a function is increasing.
In a higher dimension, a function which is going like this and this, so like the waves in the ocean. So how can we imagine that it's increasing or decreasing, sir? In one dimension, it's clear that its graph should be like in the upward direction.
So this would be the same actually. So every, you know, because what you are saying is just look at the value of the z actually. Just look at the, so like, okay, this curve is going in space, I know that. Okay, so you can assume it that it's coming out like that. Okay, imagine. But I can see that like this point has the highest value corresponding to the z. And, you know, this has, so for example, this has the lowest value corresponding to the z. This shouldn't be a problem. Okay. So s prime of t, s must be increasing. So have you remember any result when you say that if you have a function that is, you know, differentiable and, you know, its derivative is positive, in other words it's increasing over the entire a to b, then you can invert such a function actually. You can find the inverse of it. And this is pretty much natural as well. So think about it in two dimensions. So you have this function. Can you find the inverse of this function? It's not a big deal. Think about it. So here, this is the domain a to b, and this is, you know, the output side. So what would be the inverse of function? A map that takes this as the set of outputs and gives you this as the set of inputs actually. So an increasing function, okay, which is increasing over the entire domain, is invertible, is a must invertible actually. So if s is increasing, it must be invertible. So if it is invertible, then I can, okay, so s is a function of t, okay, so it's an expression in the terms of the t. So if it is invertible, I can make the t the function of s actually. Hence invertible. So I can have t as something that is dependent on s actually. So if y is a function of x and function is invertible, then x can be written as a function of some function of the y actually. So that's what we are saying there. If S is depending on t, it's a function of t, so t can be written as, and if S is invertible, can be seen as, you know, as a function of
सर
j.
सर ये सवाल है वो फंक्शन है उसमें हम सर t को डोमेन पुट करें ना फिर डोमेन कैसे फंक्शन होगा
तो ये वैसे ही हो रही है जैसे यहाँ करते हैं. How do you invert it? Yeah, that's what we mean. You know, is our understanding is well defined or not? So if our understanding is variable dependent actually, if you can recognize something with xy quickly, but you can't see that with t and s and eta xi and you know u and v, then there is more way to go actually. ठीक है, कोशिश करेंगे. We all must have. So you know, don't take that as criticism. I'm just feeling that.
सर यहाँ पे हमें जो ये जीरो वेरिएबल लेकिन हम तो यहाँ पे n डायमेंशन में हमें मोर वेरिएबल हो सकते हैं वो प्रॉब्लम क्रिएट नहीं करता
S of t is a number actually. So S is a map from where to where, A, B into some set of positive real numbers actually. So that is giving me the length of the the curve over this interval actually. Okay, so it's a real value value. So you can invert it. So when I invert it, I just gave it a name T of S actually. Okay, and this T of S is defined where? Is defined over the entire length of the curve actually, where L is the S of the scene. So think about this curve. So wherever, so S is defined where? In this manner. S of t is what? So it's like it's a function that depends on t. Okay, and it starts from A and always go to, so it's like a t is a point in the interval A to B. So we're going to say that this is defined over the entire domain. So its inverse is going to be defined where? Defined here. So that's what we will see. Okay. And the reparameterization. So if I take this P, okay, and take this T and substitute it into the S. Okay, so I'm going to say this is the parameterization of the P that is what do you call that is in the terms of the S actually. Okay, so I'm going to we call it a, when you're going to do differential geometry, we're going to call it that's a natural parameterization or arc length parameterization of it actually. Okay, and I'm going to give it a name, for example, rho of S. Okay, so this is just a formulation. So I'm interested in computing this area. That's what I would like to do. I said define S of t in this manner. I said S prime of t would exist in this manner always. It would be positive, so it's increasing. So it must be invertible. And I'm going to have a function, what do you call t of S. So the t of S is what? T depending on the S is a function defined on L. 0 to L, where the L is the length of the parameterization. And I'm saying that, okay, now take that length of the parameterization and you substitute it into the P and give that name, what do you call, the row of S. And this row of S is something very interesting. Let's talk about the row of S in a moment. So everything would be clear, don't worry about it. Okay. See that what I'm going to do is something very natural. So rho of S is this. So what would be rho prime of S if you want to? So I have this S and I would like to differentiate it with respect to S. So this is going to be d of P of T of S with respect to ds. Okay. So it's going to be P dash of T of S. Okay. And you can also see that P is directly depending on T, so I can say this is same as dP by dt, where P is the function of T of S times
Can you
dt by ds. Can I say this? It's one and the same thing. Okay. And what is dp by dt? So I can call it, this is p prime of t of s. And what would be this? dt by ds. I can see this as reciprocal of ds by dt. So I know that s of t is this, and s prime of t I already know it's basically norm of this. So I can say that this is the norm of the p prime of t of s. So what would be this value? So it's a unit vector. Okay. So this rho of s is the kind of a parameterization of the same curve C, but this is a special kind of a parameterization that has a unit speed actually. I mean, if you think about it, if you compute the magnitude of it, what are you going to get? You're going to get the unit speed. So you can see that if you parameterize the curve through arc length, it's going to be always unit speed. Okay? And if it is unit speed, let's give thing. So this rho prime of s is a function of s actually. Isn't that a function of s?
Yes.
And I'm saying that this function of s is 1. So for the moment I'm giving this function a name, sigma of s. Or maybe sigma prime of s actually. So if I call it a sigma prime of s, and sigma prime of s is this magnitude of rho prime of s, and that is equal to 1, then what you can say about sigma of s?
It will be s.
So it must be s.
It will integrate with respect to s.
So it would be like integrating this with respect to s. Okay? Since we can see that sigma of 0 is 0, because if you substitute sigma prime of 0, you're going to get, but you can see actually by definition rho of 0 is 0. ठीक है? अब आ जाते हैं सब उसकी तरफ. So what we did, bigger picture, we did a lot of calculations for a purpose. So we started with this natural estimation. We came to know, we observed, we kind of intuitively saw that this is going to distort some area, because this integral, it does not depend, the way curve is changing actually, it doesn't depend on the b prime of t. So I want to make it depend on the b prime of t. So what I want to do, I want to change this parameterization. Okay? And I'm changing this parameterization into arc length parameterization actually. So s of t is defined in this manner, computed s prime of t, inverted it. Okay, I computed a new parameterization, and then I defined what you call arc length parameterization of the path p, and then I came to this conclusion. And now I'm coming to the real part. So let's return back to that integral. So a of af actually. So what is af? Okay. Af. So af is going to be the integral. So I'm saying, do not integrate the function with respect to any parameterization, but integrate the function with respect to the natural parameterization, like depending on the s actually, arc length parameterization. Okay? So treat this as f of say, okay, rho of s, okay, and ds. Okay. So how did you got this? How did I got this actually? Okay. If I now p of t of s is what? So it's rho of s. Okay. So p of t of s, I have given it a name rho of s. So f of p of t, like f of p of t, but t is underlyingly depending on rho of s. So I can replace it with the rho of s, and you get that thing. And then I can do what? I can play a trick with it. So 0 to L, and f of rho of s and divide ds by dt and dt. Okay? Let me finally think about this integral, that what this integral is going to be. So f of rho of s is the same as, so if I apply f onto the rho of s, this is same as f of p of t, right? Because rho of s is this. So I can say that this is f of p of t, okay? And there is, so within the, there is underlying s actually. What would be ds by dt?
So it will be same.
So it's the magnitude of p prime of t, okay? And what do you say? dt. Okay? I'm writing in a very rough way. And if I make a substitution, so you can make a substitution here. So you can say that to go from here to here, I'm making a substitution s equal to s of t actually. Okay? So I'm making a substitution s equal to s of t. That will turn this integral into this integral. So not only these will change, but this limit would also change actually. So this will become a to b. Why? Because think about it. So if I take what? If I take s equal to, so I'm integrating with respect to s. If I take s and substitute 0 into it, so what you're going to get? S of 0. S of 0, would that be going to be a? Would that be going to a? We're trying to figure out the limits for yourself. Okay? So think about it. What will go on? Spend too much time on it. Finally, what does this formula is telling? So now I can put this in the form of a definition. Okay? So I could have written this definition directly without giving any intuition that what the heck I'm doing. So here's the definition. Line integral. Okay. So such kind of integrals are going to be line. When you're integrating over a curve, I'm going to call those integrals as line integrals actually. So line integral with respect to arc length. Okay? E and GTH. Okay? So this is the definition. Here, imagine I have a curve, C, the rectifiable curve, curve, okay. Parameterized by P. Okay. That is a map from say AB into Rn. Okay. And then on this curve I'm defining a map that is taking the inputs from the curve and throwing me or giving the outputs in Rn. So this would be a scalar field. Okay? So let F be scalar field defined on C. Okay? The question is, how can I integrate a scalar field over a curve C with respect to natural parameter S actually? Okay? Some people don't like to write this ds, they just write this actually. So how to integrate a scalar field over a curve C? Okay? So the definition, like this is something that we already tried. So what do? Take the parameterization of the curve, substitute it into the function, compute the speed of the function, and integrate entire interval. So that would be the line integral of the field under the curve. See, R, this is going to be the area under a curve in the space actually, that is defined through F. Okay. Area under the curve defined through S. So take the points into the speed, into the space. So f of p of t is like that. Okay. So take the curve into the space, multiply with the speed. So speed is like, so this is like getting rid of the distortion actually. Where distortion are in, if you don't resolve it, this is getting rid of the distortion. And integrate it. So you are defining a new species of integral in the terms of already existing species of the integral that we know it. So we know how to compute this integral. But through this I can compute such kind of integrals as well. Okay? खत्म करें? एक एग्जांपल करें. सोच लो. टाइम है? जल्दी है?
Sir, it means it covers two things. One, the whole length of the curve, and other thing, all the distortions or the shape of the curve. It means it covers both things.
It covers
Both things.
yes. So in other words, अगर आप so you take that curve, okay, and you try to stretch it, okay. You take that curve and split this area into the rectangles, and then what natural way we have is that ठीक है वो curve उठाएं, curvy पर्दा उठाएं and stretch it. So when you're gonna stretch it, you will see that the rectangles will be distorted actually. So some big rectangles will become small and small will become big actually. Okay, so rectangles will be distorted and hence you are losing the area. So the question is, I don't want to lose the area, so how can I compute the area under curve without, you know, losing anything? So the easiest way is, or the best way is that add this additional quantity into your, you know, integral and do the same thing. So you are doing the same integral of f of ft, but you are also adding, okay, this factor is naturally appearing, that if you want to incorporate how the curve is changing into your integral actually. That's what is the key thing. So good luck. I know it's a bit abstract.